Hello, I'm Rohan Sharma, and today we will be going through the presentation on cluster evaluation techniques. The only prerequisites for this will be hierarchical clustering and dendrograms, which will be used for one of the metrics. I've also attached a link to a website which makes these two topics slightly easier to understand if that is required. So moving to cluster evaluations for today, we start with the first metric, which is silhouette coefficient. It is a very interesting and useful metric that integrates both cohesion and separation in a way. Now, it is calculated for each data point in the data. And let's see an example here. So if point X belongs to cluster A and we have other two clusters B and C, to calculate the silhouette coefficient for X, we first calculate A, which is the average distance of points in its own cluster to X. We then calculate B. To do that, we first calculate the average distance of this point X to points in cluster B, all of them, take the average. Then we take the distances of X and points in cluster C and take that average. So we do that for all the clusters where X does not belong to, which is k-1 clusters. With these average distance values, we then take the minimum value. So we take the closest cluster to the point X. Then to calculate the silhouette coefficient, we use this formula, which is B minus A upon the maximum of A and B. Now the range of this silhouette coefficient is between -1 and 1. -1 meaning that the clustering is not good for that particular cluster. Intuitively, -1 would mean that the value of A is much larger than the value of B, meaning that the point X is much farther apart from points in its own cluster compared to the points in another cluster. Moving towards the positive values, we can say that the silhouette coefficient is for the particular cluster is good, and the maximum value of +1 can be achieved when all points in cluster A are sitting up on top of this point X. Then point X would have a silhouette coefficient of 1. Now the silhouette coefficient is basically used to compare the clustering of different clusters in the data. And on the next slide, we will see how we can interpret the chart. Now visualizing and interpreting the chart for silhouette coefficient, we have the chart on the left hand side, and we have the geometric representation of the data in 2D on the right side, the cluster marks. Looking at the chart, on the x-axis we have the silhouette coefficient values, and on the y-axis we have the cluster labels for different points. Now these points are all grouped by their own clusters, so points belonging to cluster 0 are together, and similarly for other clusters. Now the odd shape of this graph is because each line in this graph corresponds to a particular data point. So the silhouette coefficient for all data points in cluster 4 are here, and the highest silhouette coefficient is about 0.45, which is at the top, and the lowest goes into negative. Now it's important to note that the variation of silhouette coefficient values in a cluster is quite large, and this happens because some points may lie on the periphery and some lie directly at the center. It's also important to note that a minor fraction of values of the cluster 4 have negative values, and what that means is these points are much closer to another cluster compared to all the other points in its own cluster. Now we see that somewhere maybe here we see points in cluster 4 that are closer to the green cluster compared to its own cluster. Because these lines correspond to each data point, we can also see that this length of one cluster label here also denotes the number of points in that cluster. So as we see here that the clusters 2 and clusters 4 seem to have lower number of data points compared to the other 3 clusters. That can be corroborated if you look at the graph on the left, and we see that the length of the cluster label 4 here is smaller than the other 3. the cluster label 4 and 2 have a smaller size compared to the other 3 clusters. Moving on, here we also see that the cluster that's much far apart, which has a very great value, very high value B, seems to have a very high silhouette coefficient value. So basically, if we have the visualization, we can try to draw something like this. And if we have these, we can also try to draw the data with some accuracy. Moving to the next statistic that we have, it is the Hopkins statistic. It is used to answer the question, are there actually clusters in the data? Now this question becomes important because even if we give a clustering algorithm some random noise or just a random distribution of points, it will find clusters in it. For example, if we give these 100 uniformly distributed points in which there are no clusters to a clustering algorithm like k-means and give n cluster is equal to 3, it will give us this output which will have 3 clusters in it. So a clustering algorithm will always give us what it thinks is the best possible clusters in the data, even if there are no inherent clusters. Now, what this tells us is that it's very important to check if there are clusters in the data before we run any clustering algorithm. To do that, we calculate the Hopkins statistic. And the steps to calculate it are very simple. We first take the data points. We take p points from the actual data. And we also generate p points at random in the same data space. So here we look at this example and we had these gray points, which were the original points. We then selected some of the points from the original data, the blue points here in this image. So this point right here corresponds to this point. So we've selected this point. So like this, we've selected p points in the data, and then we've also created p random points, which are these red points that we've created at random. We then calculate wi and ui respectively, which are the nearest neighbor distances of the sampled points that are selected from the original data and the artificial generated points. So what we do is we place these points that are selected and artificially generated in the original data space, and then we compute the nearest neighbor distances for those. To calculate the Hopkins statistic, we just sum up these values and use this formula to calculate it. I have color coded the wi summation and ui summation just so that it can be related to this image and you can remember it well. So all the neighbor distances of the actual points are on top of the fraction, and the randomly generated points have the nearest neighbor distances along with the original nearest neighbor distances in the bottom. Now interpreting these values. So range of the Hopkins statistics is between 0 and 1. 0 meaning that the value of wi is very small. That means that the points in the actual data are much closer than the artificially generated points, which means that there are inherently some clusters in the data. A value of 0.5 is achieved when they are somewhat equal. So if wi summation and ui summation is somewhat equal, say 1, then we see a value of 1 upon 1 plus 1, which is 1 by 2, which is an exact value of 0.5. So we see this when the data matches completely with random data. So there are no clusters in the data. And the value of 1 is when the summation of wi is much larger than the summation of ui's. This happens when our data points are very, very far from each other in the original space, and the random points have somewhat a lower distance. Looking at the example, we have figure 1 here, which has data with properly separated clusters. It has a h value of 0.067, which is much closer to 0. So we would say that inherently this data has clusters. Whereas this random data, which we saw in the earlier slide, with uniformly distributed points with an h value of 0.56, which is much closer to 0.5. So we can say that there are inherently no clusters. So to say that we have clusters in the data, the value should be closer to 0. Moving to the next statistic we have, it is the RAND statistic, and it is slightly different from the other two metrics that we've seen so far. This one is a supervised measure. What that means is we need external labels for each data point to compute this value. The premise that it uses is that given that we have the original class labels of the data points, 2 points that belong to the same class should also belong to the same cluster when we perform the cluster. Moving to the steps to compute this value, we first create the ideal cluster similarity matrix, which is done using this. We take the ijth entry and put it as 1 if I and j belong to the same cluster. So after we run the clustering algorithm, we check what are all the points that belong to the same cluster, and we give them a value of 1 and others 0. Just to make it easy to understand, if we have these two clusters, C1 and C2, and C1 has P1 and P2 points, and C2 has points 3 and 4, this is what the cluster similarity matrix would look like. It would have 1 for 1, 2, and for 3, 4 because they belong to the same cluster, and for other values it will be 0. Now, one thing to note here is that the diagonal values for the similarity matrix would always be 1, and the data above it and below it will be same. So we should consider only one side of it so that we do not repeat when we are counting, we do not double count these values. Similarly, we also calculate the class similarity matrix, and that has the ijth entry of that has value 1 if points I and j belong to the same class, otherwise it's 0. The class similarity matrix would look like something like this if we had two classes L1 and L2 with points P1, P3 and P2, P4 respectively. We next compute the contingency table, which gives us the number of pairs that have the same class and same cluster, same class, different cluster, different class, same cluster and different cluster, different class. And then we compute the RAND statistic with this formula. Going back to our example here, if we calculated the contingency table for this particular data set, we would get something like this. The RAND statistic would be calculated as 0.33. Is this value good or bad? To find out, we go to the next slide where we interpret the values. Range of the RAND statistic is between 0 and 1. 0 meaning that the clusters and labels do not agree on any point of the data, any pair of the points. And as we move towards 1 would mean that clusters and labels agree on all points, all pair of points. Now, this is inherently because we have F00 and F11 in the numerator. And if this value is 0, that means that the sum of these values is 0. So same class and same cluster is 0, and different class and different cluster is 0. To look at a few examples of RI values, we look at the following data sets. The actual data set is on the left hand side with their class label colors, and the cluster data is on the right with the cluster label colors. We see that the RI value is 0.33 for this clustering. This is probably because the cluster right here, the yellow cluster, is the points here belong to a different class compared to points purple, but here this clustering algorithm clubs them as together, so we get a low RI value. Looking at the RI value of the next data set, we see that it's almost perfect, and I think it is only missing this data point which it has not correctly clustered. Moving to the next data set, we have a perfect RI value of 1, and it exists when all the class labels match exactly with the cluster labels. Now it's important to see that the color here is slightly different, but that is because we use classes and clusters use the same labels, 0 and 1, and it's not necessary that the label has to be same. It's just that they need to belong to the same cluster and same class. Moving to the next question that we have on this is that a data set after clustering has a RAND statistic value of 1. What will be the off diagonal values of the contingency table? So basically, if we have something like this, which has an Ri value of 1, what will be the value of f11 and f00? Well, clearly, if they agree on, if the classes and clusters label agree on everything, then these points will have, okay, so what will be the off diagonal? So f11 and f00, so they will have zero zeros in f10 and f01. Similarly, if we have a data set with random value 1 and we have the ideal class matrix, what will be the ideal cluster similarity matrix for that? So because they have to match on everything, it will have the same matrix for this. Moving to the next metric we have, it is the Copernic correlation coefficient. It is used to evaluate how well hierarchical clustering algorithm works on the data set. And to calculate it, we just find the correlation between the original distance between all the points and the Copernic distance. Now, Copernic distance between 2 points is the distance between them just before they were merged. So at that stage of agglomerative clustering where these 2 points are supposed to be merged, what is the distance between them? That is defined as the Copernic distance. To visualize it more easily, we look at this example here. Say, for example, in a stage of agglomerative clustering, we see that AB are in a cluster, CDE are in a cluster, G and I are in a cluster, and H is not in a cluster. So we see that the distance between cluster AB and CDE is 0.5, and turns out that it is the lowest across all. We then look at, so we will be merging AB with CDE. So 0.5 is the distance where we are merging. Hence, the Copernic distance between A and C, A and D, A and E will all be 0.5. And similarly, it will be 0.5 for B2. We then calculate the Copernic correlation coefficient, which is the correlation between the Copernic distances and the original distance matrix. The range of this metric is between -1 and 1 because it is a correlation coefficient, but more often than not, you'll see that the value lies between 0 and 1 because it is a correlation between 2 distances which kind of use each other because original distances are used in agglomerative clustering to find the distance between points, and then thus Copernic distances are somewhat related to it. So we mostly see values between 0 and 1. Now, a negative value or a value near 0 would mean that the clustering does not fit the data well, and a value of closer to 1 would mean that the clustering technique used fits the data really well. Looking at a few examples, we have a toy example for computing the Copernic distance matrix from the sample dendrogram. So, for example, if we had a agglomerative clustering which had the following dendrogram, how can we get the Copernic distance matrix from it? Now, dendrogram is something that tells us at what stage do 2 points are merged together. And looking at this, we see that AB, points AB are the first to get clubbed as a cluster, and then they are clubbed to point C. So how to fill this table right here, which is the Copernic distance matrix? We first look at AB. We see that the distance between them is 10 when they are put in a cluster. So distance between AB will be 10. We then see that they are merged with the point C at a distance of 12. So C is merged with B and A at a distance of 12. So the Copernic distance between C and B will be 12, and C and A will also be 12. It's important to note that the original distance between CB and CA is not necessarily to be the same, but when we are computing Copernic distances, because they are merged as a cluster with C, the distance between AB and CB, CA and CB will be same. Similarly, we calculate the Copernic distance for the other points, and we get the Copernic distance matrix. To calculate the coefficient, we then calculate the correlation of this matrix with the original distance matrix. To give an example of how we select the best agglomerative clustering technique using this value, we look at the following table, which has the linkage method that we used or the algorithm that we used for agglomerative clustering and the corresponding Copernic correlation coefficient. We see that we find out the best value, which is closest to 1, and we select that clustering because that clustering suits the data best among these three. So because among these three, average link has the highest value and which is closest to 1, we pick that value. So to summarize what we have learned in this presentation, we start with the silhouette coefficient and we found out how it is calculated for each data point. We also saw how the chart of the silhouette coefficient is interpreted and how we can find out which cluster in the geometric representation refers to which part of the chart. We also looked at what is the range of this particular coefficient and what values are best for clustering. We then moved to Hopkins statistics, which is required to check if there actually exists some clusters in the data before we do the clustering. And we saw how it is calculated using a random generation of points and then comparing the nearest neighbor distances of actual points and the random points. We also looked at what is the range for this value metric and what is better for clustering. We then also looked at the rand statistic, and in that we learned how to compute the ideal cluster and similarity and class similarity matrices, and how to fill the contingency table, and then how to finally calculate the rand index, and looked at also the range and which is better for clustering. Finally, we looked at the correlation coefficient, and we found out that it's used for comparing different hierarchical clustering techniques. We also saw how it's calculated and what is the range of this metric. We also saw that the values closer to 1 are inherently better for clustering. If you've reached this far, I'd like to thank you for your time. If you have any feedback or questions, please reach out to me at my mail ID, which is given here. I'd like to thank you again.